Tens of millions of red crabs crawling their way to the ocean as part of an annual migration on Christmas Island, Australia.
An island so famous for its oceans of bright red crabs that the ground practically moves every year is suddenly going silent. How is that happening? Well, tiny yellow crazy ants, so small you could crush them with a finger, have powerfully wiped out 40 million crabs like it's nothing. And trust me, their attack method? It's straight out of a nightmare. This is one of the most dramatic ecological stories you'll ever hear. Is this proof that sometimes the smallest heroes can hit the biggest worlds? Stay with me, because this story only gets crazier from here. Yellow crazy ants devastate red crab populations. The invasive yellow crazy ant, known scientifically as Anoplolepis gracilipes, reportedly became one of Christmas Island's most destructive forces, a silent takeover that shocked scientists and locals who never imagined that such tiny insects could reshape an entire ecosystem so violently. According to researchers, these ants caused the deaths of tens of millions of Christmas Island's iconic red crabs, and the loss of those crabs created a chain reaction that touched every corner of the island's forests. The ants reportedly used an unusual and frightening method of attack, something described as chemical warfare rather than the usual biting or stinging seen in other ant species. Experts explained that yellow crazy ants sprayed potent formic acid directly into red crab eye stalks and leg joints, a tactic that blinded crabs instantly and weakened them beyond recovery. Could anything be more terrifying than a creature losing sight while surrounded by thousands of enemies? The panic, the chaos, the sheer survival instinct kicking in as every step becomes a gamble. That's exactly what the scientists faced as they watched the ecosystem teeter on the brink, dominated by an unstoppable swarm. What happened next didn't just shock the researchers, it transformed the entire island. Stay with me, because every moment of this story is unlike anything you've ever seen. As reports described the scene, the crabs tried desperately to wash off the acid, only to suffer dehydration, confusion, and exhaustion until collapse. In areas where up to 1,000 ants occupied a single square meter, the formic acid concentration reportedly became overwhelming, giving the ants total control during mass attacks. After crabs became immobilized, the ants, according to field observers, would tear the helpless animals apart piece by piece, making these events some of the most shocking natural predation scenes recorded on the island. Researchers described the red crab as a keystone species, explaining that the entire forest once depended on this single organism to stay healthy. The crabs constantly burrowed through soil, loosening it and allowing air and nutrients to circulate. The droppings left behind by the crabs reportedly acted as natural fertilizer, and every day these animals cleared enormous amounts of leaf litter from the forest floor. Could anyone imagine a forest where millions of leaf-eating creatures were suddenly gone? Scientists warned that the loss of crabs meant the forest floor stopped being cleared, causing leaf litter to pile up in thick, suffocating layers. Without the constant grazing of crabs, seedlings sprouted uncontrollably, and areas once open and easily navigated became dense, tangled thickets. Soil compaction reportedly followed as abandoned crab burrows collapsed, removing microhabitats that supported countless other species. In some places, experts described forests that once held birds, insects, plants, and small animals as nearly empty, with little remaining besides yellow crazy ants and their expanding trails. Could a forest really lose its character so quickly simply because one species vanished? Reports suggested that this was exactly what happened, a complete ecological unraveling triggered by the ants' relentless advance. Historical accounts indicated that yellow crazy ants arrived on Christmas Island sometime between 1915 and 1934, likely through shipping activities. For decades, their presence seemed harmless, and no major ecological disruptions were recorded. The situation changed dramatically in the 1990s when the ants suddenly began forming supercolonies, a phenomenon unlike anything previously observed on the island. These supercolonies covered vast stretches of land, sometimes extending across hundreds of hectares. One supercolony discovered in 2002 reportedly spanned nearly 1,900 acres, an almost unimaginable concentration of ants in one location. What allowed such explosive population growth? Researchers pointed to the species' unusual cooperative behavior. Unlike most ant species that fight rival colonies, yellow crazy ants reportedly recognized one another as part of the same extended population and refused to engage in territorial battles. Could cooperation on such a massive scale really give insects this much power? Scientists believed so. With endless food sources, no natural predators, and no inter-colony fighting, the ants expanded freely, reproducing in numbers that reached into the billions. Observers explained that this unity allowed the ants to move as one giant organism, overwhelming anything in their path. Experts later explained that the invasion did not just represent an increase in ant numbers, but a complete restructuring of ecological order on Christmas Island. Once the red crabs disappeared from certain areas, the forest began changing at a pace no one expected. Leaf litter built up so rapidly that decomposition patterns shifted, altering nutrient cycles and moisture levels. New plant species began to dominate, while others vanished. Animals that relied on open forest floors either migrated or died out, unable to adapt to the thick vegetation that now covered large portions of the island. Many researchers asked whether the island's ecosystem could ever return to what it once was without the crabs. Reports emphasized that the ants acted as ecosystem engineers, but in a profoundly destructive way. Instead of creating new ecological balance, they dismantled the old one, leaving damaged, simplified landscapes behind. As scientists continued documenting the crisis, many described the situation as one of the clearest examples of how invasive species can destabilize entire ecosystems. Observers asked how such small insects could overpower such large crabs, reshape forests, and dominate huge territories in such a short time. The answer, they reported, lay in a blend of chemical weaponry, cooperative strategy, lack of predators, and unusual density that no native species could counter. The yellow, crazy ant invasion became a powerful reminder that ecological systems can collapse quickly when key species disappear. Could a single ant species truly change an island so completely? Researchers insisted that Christmas Island offered undeniable proof. The story of the ants and the crabs on Christmas Island reveals just how fragile natural systems can be. One small shift, one overlooked interaction, and an entire ecosystem can teeter on the brink of collapse. At first glance, it seemed almost surreal. The crabs, once rulers of the forest floor, suddenly facing an unexpected threat from tiny invaders. But as researchers dug deeper, they uncovered a hidden catalyst, a microscopic player that was quietly fueling the chaos. Scale insects, seemingly harmless at first, became the perfect fuel for the explosive ant invasion, creating a chain reaction no one had predicted. This delicate dance between species, predators, and parasites showed how quickly balance can be lost, and how the future of an entire ecosystem can hinge on the smallest, most overlooked forces. And this is just the beginning of the story. Scale insects fuel the ant invasion. Behind the explosive growth of yellow, crazy ant populations reportedly lies a strange and powerful ecological partnership that many people would never expect, one that quietly built the perfect conditions for an environmental crisis on Christmas Island. Researchers explained that the entire chain of destruction began with the arrival of yellow lac-scale insects, tiny sap-feeding bugs called Tacardina aurantiaca, which cling to tree branches almost the way barnacles cling to rocks. These insects settled into the island's forests and multiplied with surprising speed after arrival, mainly because nothing on the island hunted or controlled them. Would anyone imagine that such small, simple insects could reshape an entire ecosystem? Scientists said the bugs feed by tapping straight into tree sap, and once fully mature, they release a sweet liquid known as honeydew. This sugary liquid pooled on the leaves and branches like little droplets of syrup, and that sugary resource soon became the spark that changed everything. The absence of predators allowed the insects to reach massive populations, turning the island's trees into a non-stop honeydew factory. At first glance, it sounded harmless. What trouble could a little sweetness cause? But that honeydew supply created perfect feeding grounds for yellow crazy ants, a species already known for unusual behavior and extreme colony sizes. Researchers explained that the ants formed a mutualistic partnership with the scale insects, a classic biological arrangement that benefits both sides. In this relationship, insects produced honeydew from anal pores, offering ants a rich and steady carbohydrate source. In return, ants acted like protective bodyguards, shielding scale insects from whatever threats might appear. Experts described it almost like the relationship humans have with livestock, only smaller in size and far more destructive. Could a tiny drop of sugary liquid really supercharge an ant colony? Laboratory studies answered that question clearly. The carbohydrates gave ant colonies a dramatic boost in population growth, foraging energy, and general aggression. Scientists reported that for yellow crazy ants, the honeydew is so important that its weight makes up nearly half the weight of an adult worker. With such a constant fuel source, the ants spread at a breathtaking pace, eventually forming supercolonies that packed more than 2,000 workers into a single square meter. Researchers said this density created a living carpet of ants that overwhelmed other species, wiped out native red crabs, and disrupted the island's natural balance in a way few had ever witnessed before. It raised the question, how could any ecosystem withstand such a relentless invasion once it gains momentum? The partnership grew so strong that scientists began asking what might happen if the ants ever lost access to the insects that sustained them. Could such an unstoppable population crumble without the sweet liquid it depended on? To find out, researchers conducted controlled field experiments where they blocked ant access to the tree canopy where the scale insects feed. The results, according to field reports, were immediate and astonishing. Colonies that suddenly lost their honeydew source collapsed with alarming speed. In some areas, ant populations reportedly fell by 80% in only a few weeks, while activity on the forest floor dropped by 95% within a month when honeydew access was removed. That rapid decline proved something critical about the ants. The entire invasion machine depended almost entirely on a single food source. Once that source disappeared, the aggressive growth, the massive numbers, and the supercolony behavior vanished just as quickly as they appeared. Researchers described the dependency as both the strength and the weakness of the species. Could such a destructive force really fall apart because of one missing ingredient? The results suggested exactly that. Without honeydew, ant colonies could not maintain the enormous numbers required to dominate the island. This discovery opened the door for targeted control strategies that focused on disrupting the partnership instead of attacking the ants alone. By weakening the scale insects or breaking the connection between insects and ants, scientists believed the entire ant population could collapse naturally. In many ways, the relationship that once fueled devastation also held the key to recovery, revealing a path forward that no one could have predicted. On Christmas Island, the chaotic dance between the yellow crazy ants and the invasive scale insects had turned the ecosystem upside down, leaving forests decimated and native species on the brink. Yet nature often has a hidden resilience, and scientists began to see that the very chain that caused so much destruction could be carefully disrupted to restore balance. By identifying the critical link, the scale insects that fed the relentless ant colonies, researchers realized they could intervene strategically. This insight led to a bold, delicate experiment. releasing tiny parasitic wasps that target the scale insects, undermining the ants' food supply and breaking the cycle of devastation. What unfolded next would redefine how we fight invasive species. Keep watching till the very end. Scientists release parasitic wasps to break the cycle. After pinpointing the crucial link between the invasive yellow lac scale insects and the destructive yellow crazy ants, scientists reportedly developed what they called a strategic biological control plan. And in 2016, Parks Australia introduced a tiny Malaysian micro-wasp, Tachardia ephagus somervillei, measuring barely 2 millimeters in length, to Christmas Island, with the goal of targeting the scale insects that had been fueling the ant super colonies. Experts explained that the wasp operates as a parasitoid, a type of insect that lays its eggs inside mature female scale insects, allowing the larvae to develop within the host and eventually kill it from the inside out. Could such a small creature really take on an invasive pest problem of this magnitude? Researchers observed that once the larvae matured into adult wasps, they immediately set off in search of more scale insects, creating a self-perpetuating control cycle that required no ongoing human intervention after the initial releases. The approach seemed elegantly simple, yet relied entirely on precise ecological knowledge, with one scientist reportedly noting that every detail of the wasp's behavior had to be understood before trusting it to do its job in the wild. The choice of Tachardia ephagus somervillei was deliberate, as researchers highlighted that this particular wasp naturally preys on the yellow lac scale insect in its Southeast Asian home. The wasp's name itself, meaning eater of Tachardina, reflected this highly specialized role. In its native range, the scale insect is reportedly rare because of the wasp's effectiveness, which gave scientists confidence that it could suppress the same pest on Christmas Island. Moreover, careful studies showed that the wasps could continue attacking scale insects even in areas dominated by aggressive yellow crazy ants, which had previously made control measures nearly impossible. Could such a tiny wasp really navigate environments swarming with super-aggressive ants and still successfully hunt its host? Researchers acknowledged that understanding this interaction was critical before committing to any release. Before introducing the wasps to the island, the team conducted extensive host specificity trials in Malaysia, exposing 8 closely related species of scale insects to the wasp and confirming that none were affected. This careful research, along with rigorous biosecurity checks and governmental risk assessments, ensured that the wasp would not become another invasive problem. The Department of Agriculture and Water Resources reportedly published the final risk assessment in September 2015, giving the go-ahead for the release. Scientists emphasized that no step could be rushed, as a single miscalculation could have unforeseen consequences for the island's delicate ecosystem. Could anything have gone wrong despite all the careful planning? The stakes were high and every precaution had been taken to make sure the intervention targeted only the intended pest. Once the wasps arrived on Christmas Island in December 2016, researchers from Parks Australia and La Trobe University began breeding them in captivity until populations reached numbers sufficient for release. A total of 167 wasps were initially brought to the island, but the plan aimed far beyond the small starting population. Researchers eventually released around 18,000 wasps across 4 of the largest yellow crazy ant supercolony sites, including Grants Well, Blowholes, Margaret Knoll, and Circuit Tracks. Observers were reportedly amazed at how effectively the wasps spread under their own power, with some traveling up to 1.5 kilometers beyond the original release points. Could a 2mm wasp really travel that far and remain effective in such challenging terrain? Scientists noted that the wasps' rapid dispersal and continued hunting of scale insects allowed the biological control effort to take root without ongoing human management, and early results suggested a marked reduction in scale insect populations which in turn weakened the yellow crazy ant colonies. The strategy was described as a rare example of an elegant, self-sustaining ecological solution, a demonstration of how understanding the precise relationships in a complex ecosystem could produce results that chemical sprays or manual eradication could never achieve. Researchers reportedly continued monitoring the sites, studying how the wasps adapted to the new environment and tracking the long-term impact on both the scale insect and yellow crazy ant populations. Could such a small intervention really tip the balance in favor of ecological recovery? According to reports, the micro-wasp program became one of the most closely watched biological control experiments in the region, with scientists documenting not only population changes, but also behavioral interactions among species, soil health, and vegetation recovery. Observers noted that, unlike chemical interventions, this approach allowed natural predator-prey dynamics to reassert themselves, restoring a measure of balance to areas previously dominated by destructive ants. Every detail of the program, from initial host specificity trials to the precise timing and location of wasp releases, was reportedly designed to maximize effectiveness while minimizing risk. Over time, the success of the micro-wasp initiative reportedly became evident as scale insect populations declined dramatically, which in turn reduced the food supply for the yellow crazy ants. Scientists described this indirect effect as one of the most satisfying outcomes, a demonstration of how a tiny creature could produce outsized impacts on a fragile ecosystem. Could a 2-millimeter wasp really change the course of an entire island's ecological future? Observers marveled at the efficiency of the process, noting that by targeting the very foundation of the invasive ant problem, the micro-wasp strategy addressed the root cause rather than simply attacking the symptoms. Researchers emphasized that while challenges remained, including monitoring long-term ecological consequences, the project represented a model of science-driven environmental intervention and offered hope for similar invasive species challenges elsewhere in the world. With this, we have come to the end of this video. Thanks for watching. If you enjoyed this video, do well to like, comment, and subscribe for more content. To enjoy more thrilling stories, click now on the following video that pops up on your screen.